Okay, hello. My name is Jason Shankel. I'm a senior gameplay engineer over at Roblox. And I'm here today to talk to you about monads and monadic design and how they are impacting the discipline of software engineering in the modern era. So before I begin, I just want to take a little survey here real quick. How many people have heard of monads, heard the phrase monad? Okay, so a little bit, they're starting to get popular, but how many feel like you have a grasp of what they are and can kind of understand and explain? Perfect. Okay, so that's what I'm here to talk to you today about, is what monads are and why they have become popular in the last couple of years. So to understand the role of monads in modern software engineering, the first thing you have to grasp is the difference between functional and imperative programming and how these two disciplines have struggled throughout the years in both academia and in industry to be the dominant view. So once again, a little survey. How many people imperative versus functional programming have seen and heard about it? Okay, good. So basically, when you ask a functional program what a monad is, this is the typical standard monad joke. That a monad is just a monoid in the category of endofunctors. What's the big problem? And this is the typical response from an imperative programmer, which is just say monad one more time. You're just using this as an excuse for what you're trying to do. So what functional programming and imperative programming are two models of how we think about the execution of instructions on a system that have evolved from this probably before the 60s, but certainly since the 60s. And the basic idea is that the imperative programmer is programming the machine directly. The machine has a certain behaviors, it has a certain state. You know the instructions for that machine. You execute an instruction, it changes the state of the machine. You rely on the machine now being in that new state, and you move your life forward that way, doing your programming. And this has been the dominant model for computer programming in industry for certainly as long as I've been in, like that. Functional programming is a more mathematically pure and abstract notion of programming, where you're not instructing the machine directly what to do moment to moment, but instead you are telling it big picture what you want. You know, take this list, give me all of the elements that satisfy this condition, transform them all into strings, parse these strings into some other kind of record. Just do these things in a chained order. And in functional programming, what you are looking for is, unlike imperative programming where every step changes the state of the world, in a purely functional program, functions have no side effects. If you call a function with a parameter, you'll get a particular value, you'll get that same value again. No state is changing. Nothing gets updated when a function gets called. You just get a value right back, and you chain all of these functions together until you get the final value you want, and then you use that to maybe change the state of the world or to set a record or something like that. So the problem with functional programming as an industry standard for a long time has been one that it's basically impossible not to have programs that don't have side effects. It's very easy to avoid the problems of imperative programming if you simply don't produce results, right? And so that's been one of the criticisms of the functional approach, is that you're insisting that everything I build have no side effects whatsoever. Well, Pocket Calculator, has side effects. When I hit a 5, it ends up in the input register. I've made a change to the world. How can a functional program handle that? And the answer has been monads. And then somebody draws a gun and say that one more time. Say monads. Okay, so basically, I'm going to dig in a little bit on the way that imperative versus functional kind of works. Here's an example of a problem done imperatively in C#. For retrieving the number of male patients of all the doctors in a hospital who are on staff, right? So I want to go to all doctors who are on staff, get all of their male patients, right? And so this kind of looks like the way you would do it traditionally, probably if you were an imperative programmer, where at each step you are telling the system specifically the thing to do, and then you've solved the problem of how you work this out. Work out getting this list, and you've told the computer precisely how to do it. So get all current patients, takes an array of doctors, right? It makes a return array of patients. These are record types. For each doctor, it says if the doctor is not on staff, then skip him. Otherwise, go to that doctor, and for all their patients of that doctor, if that patient's gender is male, then add that patient to the return list and then return the return list at the end, right? So you've probably done something like this if you've done a little bit of programming. And you'll notice that in the middle of all this, because I'm going step by step and saying, here's how you do it. You empty this list. You go walk through this list. You go through everything in this guy's list and put it into that list. I can also do any old hack I want. Like I can increment a hack integer that's sitting there that says, okay, well, there's a total number of patients ever added to any list, gets incremented every time I do this. Somebody else in some other module somewhere can be listening on that. And when it reaches a certain value, it could decide it's going to purge the database or have some other side effect. So this highlights one of the great dangers of imperative programming, in fact, the key danger, which is that because you're changing the state of the machine on every step, you can change something global. You can change something that somebody else cares about, and that can change the way that things work in your program. And in the past, this has been our major source of bugs, but we've been able to deal with it because we're dealing with very, very small machines with single cores where we're owning practically everything that's going on. So if you mess up something that somebody else is listening for, it's a relatively straightforward manner to, a matter for you to go and clear up your own code. Nowadays, we write little tiny apps that run on giant shared systems with very complex interoperating systems, and so simply relying that your code with side effects will be treated well by the rest of the system is less reliable today. So here are the elements in imperative programming. First of all, you get precise control over the execution and resource usage, as I said. So you can tell the chip exactly what to do, what piece of memory to go, like that. You're close to the metal, and computers are inherently imperative machines, right? So a modern computer is a block of memory and a bunch of peripherals and hard drives and a bunch of processors that draw the memory down into registers, perform math, put them back in the memory, put them back on the drive. The system itself is inherently just going step by step and changing its own state. So imperativeness puts you close to the metal. These are all sort of the reasons why imperative programming has dominated software engineering, at least in the business world. You can do side effects, and you can have changes of global mutable state. That's like the #1 source of bugs in an imperative program is I made a change over here that somebody else is going over here. And if we're in a multi-threaded system where on some computers we might have just one core that's sharing time between two processes, on another system we might have two cores that are running exactly the same time, that's slightly different. So my side effect behaves slightly different on slightly different hardware. This is the kind of bugs that plagued us throughout the 90s and 2000s as systems got more and more complex. And it became more and more difficult for us, even in game development, to really control the metal and decide how chips are going to work. Even if you could do that, you can't beat the OS for scheduling things, so you kind of don't want to. The other big source of bugs in imperative programming is the order of operations. Because, once again, with threading, if it matters what order you do things in, and two threads might be doing things in two different orders, you can end up with different results based upon a very small change in code. So in order to compensate for the trials of imperative programming, we developed breakpoint state-based debugging. How many people have used Visual Studio or Xcode or MonoDevelop? Okay, so you guys kind of know what you do when you run into a problem is you set a breakpoint, you run to that point, you have your watch windows, you see your states of your global variables, what changed. Maybe you have a trace window where it says, well, I did this, and I did this, and I did this, and now I'm here. You look at your call stack. But basically, the entire tool set for modern interactive development environments is based on the idea that you're going to want to stop on an instruction and see the state of the machine because you're doing things imperatively. Right? So somehow I ended up in a bad state when I was here. I'm in an unexpected state while I'm here. Why? Is the basis for your analysis. What happened there? Okay. So in order to manage all this complexity and to manage like the flood of especially as in the 90s as things became interoperable and component based, we developed object-oriented design programming and then design patterns in object-oriented development, which once we accepted the object model, then the design patterns came along that said, well, here's how you use it without tangling yourself up in yarn too much. And we've, since the 90s, kind of taken this, in fact, I started speaking here based on discussing object-oriented design patterns. Because what object-oriented design patterns allow you to do is to isolate your code so that your side effects have fewer effects on the global system, so that so that an object can publish a contract and say, if you call me with this value, I guarantee you that I will, fulfill these parameters, and I won't mess with these values, and I will mess with those values, and those kinds of things. And all of this has led to a scenario in software engineering that Steve Yege calls the kingdom of the nouns. I highly recommend, check him out, Steve Yege. He's a blogger. Most of his, I don't know if he's written anything in a while, but he wrote some great posts about 10 years ago. And one of them was the kingdom of the nouns. And what he said here is that this model that I've described to you, this kind of imperative programming that led to object-oriented programming and object-oriented design patterns, is based on, he created a little allegory for it, called the kingdom of the nouns, where he said, look, imagine you had this realm where you had two kinds of beings. You had nouns and verbs. And nouns are first-class objects. They can wander around, they can do whatever they want, they can be addressed, they can be assigned to variables and passed about. But verbs cannot. A verb must always have a noun chaperone. Okay? And so that's the kind of space we went to in C++ and Java and C# and all these object-oriented languages, is that the top-level being in any of your programs is a noun of some sort, some object, an object manager, a manager of managers, a list of object system interfaces, right? And those are all these basically these nouns, quite often singletons, right? And if there's a verb that you want to do, like, set off a firework or send a message or shut down a queue or read something off of a network, it has to be a member of an object. Right, so we have some object called network manager, and it'll have a member function called update network or whatever. If you want to just pass update network around all by itself, that doesn't happen. And that's kind of what has shut functional programming out. This mindset has shut functional programming out of industrial software development for decades, because pretty much we do all of our designs from top down, thinking about objects and object relationships, and not thinking about verbs, and not thinking about the way that functional programming thinks about verbs. Okay, so the rise of the verbs in functional programming. Here's what our Doctor project, our Doctor function looks like using the link library in C#. But there's other libraries in JavaScript that are similar to this. Scala is based on this entire approach. So it's all over the place basically. And in the rise of the verbs, what we say is that we're no longer going through and saying, give me each noun. Okay, for each noun, go get me its subnouns. Okay, for each of them, put it into another noun and pass it around. Instead, we just have these fairly simple filter functions that take lambda operations and use them to produce varying results. So here we have, again, the patients, the male patients of doctors who are on staff at a hospital, all the doctors, where, okay, and where is in C# the equivalent of filter in JavaScript or like that, which basically says, given this list, give me a list where this statement is true for each member of the list, right? So we're saying for doctors where, and what this is a lambda function. Now, how many people have seen lambda functions at all? Okay, good. So what a lambda function is a liberated verb. It's a function that just lives on its own without a noun chaperoning it around. And this is the syntax for a lambda in C#. It says there was some function that takes a single parameter d, and it is bound to this operation. Just return if d is on staff or not. That's it, right? So this is a function that returns a Boolean, and that Boolean is this on staff for whatever parameter it's passed. And we take that function, and we send it into the list of doctors. And it goes over every doctor, and it says, is it true for you? Is it true for you? Is this function true for you? And if it is, then we tack it onto the list that's going to come out the other end of this thing. All right. And now, with one function where we can filter based on any number of criteria. And in fact, in C#, since it's a mixed mode language, this lambda can have global side effects. It can go poke a hack value if you want it to. However, if you're doing things functionally, it would not. This lambda function would have no side effects whatsoever. Okay, comes out the other end of where is a list of doctors who are on staff. And now we call select many. And what select many is a function that takes a list of objects and a function that takes an object of that type and produces a list of some other type. Okay, and select many in C#, which is the equivalent of flat map in Scala, or a map called followed by a flatten call in JavaScript, is the basis for monadic design. Okay, these functions that say give me a single object or a list of objects, and then a function that takes one of those things and produces a list of something else. Do that for each thing, take all of those lists and flatten them out. So what this is doing is saying, out of all of the doctors who are on staff, here's a function that takes the parameter one doctor and says for that doctor's patients, where the patient's gender is male, return that. So we get a list of all the male patients for each doctor one at a time, and then we get this list of lists, and then that list of lists is flattened to just one big list. And of course, we're not checking for duplicates here, so if a patient has multiple doctors, they'll show up in the list multiple times. You know, we can solve that in other ways. But that's basically the functional programming approach to this. Now, the advantages of this. First of all, it's concise. There's no ceremony here that you don't need. There's no setting up a return value, poking values into it, doing my own if statements and all this kind of stuff. I'm flatly and plainly speaking my intent. Doctors, where the doctors on staff, give me the patients where the patients are male. That's it, right? It flows a little bit better than an imperative implementation. There's no shared mutable state here. Now, like I said, in C# there can be here. These lambdas can talk to global mutable state, and things could happen. But in a in a pure functional language like Haskell, you wouldn't be able to do that. You can have black box algorithms that are highly optimized for rapid searches over what are called list comprehensions and things like that. You don't have to figure out the best way to iterate in this particular library. You know, the library implementers can do that. But you're also giving up control of how things are done. If it matters to you how we iterate over doctors and patients and things like that, then this might not be the approach for you. But 99 times out of 100, it doesn't matter, and 99 times out of 100, you're not going to beat somebody whose job it is to write the most, efficient list comprehension functions that they can. Now, the problem is that the world is still imperative. With a pure functional system like this, you can't even write so much as a pocket calculator, because it's great that you got this return value. It can't go anywhere. You can't poke it anywhere. You can't store it anywhere. You can't do any other kind of thing. So that is, so what we do is we end up in functional systems having places where we make an imperative step. We say, we're going to do this big functional calculation, then we're going to take the results and we're going to write it to a database. We're going to put it into memory. We're going to close our eyes and do something imperative. And that has been, just as unstructured programming was a problem in imperative programming, the kind of like hand waving of changing global state because it has to happen, but more or less obsessing over the whole places where we're not changing global state, leaves you, is a good direction in functional programming, but it leaves us with not enough tools for understanding how to write complex and robust systems. Okay. It's very difficult to do breakpoint-based debugging on this. And you don't typically find yourself in the middle of an operation. You find yourself having completed one step of a comprehension. So debugging tools have had to be developed that are more based on traces and tests and exception paths and parallel computations that follow the first one and say, oh, you tried to do this and you tried to do this and then you added this and you didn't add that for that reason. It makes a record of everything, of every choice that gets made or whatever. But you basically end up doing a lot more reading of printouts and say what just happened instead of stopping at one point and saying what state are we in right now. Because quite often, especially in highly lazy systems, there's no great way of knowing what state you're in right now. Because the only reason you're in a state is because you asked what state am I in a lazy system. I'm not going to evaluate anything until you ask for it. So if the debugger asks for things that wouldn't have gotten asked for, then you get this Heisenberg quality where by merely looking at the bug, you've changed the way that it behaves. Right. So to deal with those problems, the problems that come into functional programming of lack of traceable state and lack of ability to really understand how errors propagate, the functional programming world embraced something called monadic design. It provides interoperability and state management, and it does for functional programming what object-oriented programming did for imperative programming. It takes the problems with it and contains them in a well-understood area. Okay, so what is this monad thing that I'm talking about? Well, so what I would like to do is I would like to be able to tell you that in professional software development, what happens is we work for a while in a particular model, and then along comes a new paradigm that somebody's described, and it's just so clear and so correct, and this is how we got into object-oriented development, and now this is how we're embracing functional programming because it's just the right thing to do. But that would be what we call in the industry a lie. We do not adopt new ways of thinking about problems and new ways of doing things because they're better. We adopt new ways of thinking about things because the platforms change on us. And in our world, the platform is the paradigm, right? And when I was coming up, in the 90s and whatnot, the dominant platform was the desktop PC and Mac, right? Typically single core systems, running fairly slowly, where you really had to care about the operation of the machine. And so at that time, it was lunacy to suggest that you would be using a virtual machine or a just-in-time compiler on performance consumer software, especially like a video game or something like that. It was, we were debating about whether we could afford virtual functions, and so there was no way that we would even consider like writing a game in Java in the late 90s, unless it was purely on the web or something like that. Nowadays, just-in-time compilers and virtual machine performance are through the roof. Right? It's the Java virtual machine, the C#, the .NET system, very, very fast. And just-in-time optimizing compilers for each platform are going to beat your hand-rolled thing that you're going to do on each platform. And the platforms are changing so rapidly that if you actually decided to go out and hand do the assembly for an app or something like that, within 2 generations, your code will be completely useless, where other code that can be compiled just in time will, be updated to the new hardware when it gets recompiled. Okay, so for practical mercantile reasons, for reasons of making money, virtual machines and just-in-time compilers suddenly became viable, right? Because we're no longer dealing with these really underpowered systems where we have a lot of control over the individual hardware. We have opaque systems that are much more powerful. The other thing is that a lot of the problems that we're facing now lend themselves to lazy evaluation. Back in the day, we didn't really think to even ask about data that we didn't need for stuff, right? In a video game, you just say, give me everything that's within this frustum and let me just render it and I'm done, right? Whereas with app development, a lot of the big data stuff we're seeing now, if you're searching for all of the Starbucks that are in this area, or a big data problem on your map, chances are you're going to be getting a bunch of results that you don't really want yet. You just want to see what's on the screen or what the person has asked for or whatever. And so functional programming, because there are no side effects, because you know that your functions do not affect the global state, they don't change anything, then it doesn't matter what order they're called in. Right, or by who. It's just every time I call this function, I get this result back, and that's it, and nothing else has changed. And because of that, that means I don't actually have to call a function until I really need that value, because there's no timeliness involved. Nothing's going to change that's going to change the way that I behave. So until you actually need my value, I'll just wait around. I'm not going to actually evaluate until that value is needed. Now, there's ways of doing this yourself imperatively, saying, okay, I want to create a new thing. It's called lazy result, and a function that sets up an instruction package for a lazy result, and I'll go check my lazy result and see if it's evaluated, and if it's not, I'll say eval because I need it. You can do this stuff. It's just that you have to do all the ceremony yourself, and you have to be smarter at it than the developers of Haskell, right? And you have to be better at it than teams whose whole life is dedicated to solving just that one problem, and you're not going to be, right? And then finally, with multi-core systems, now we have you guys have phones that have 4 or 6 cores on them or whatever. Back in the day when we only had 1 core, well, okay, side effects were fairly easy to manage. Once we started getting 2 or 3 cores and we started threading a lot, well, now we have all of our code is running at the same time across multiple things. If, as I mentioned, if they're poking global state, depending on when this guy did his work and then this guy did his check, things could end up very, very differently. In functional programming, because there are no side effects, the code that's inside of a side effect-free, a pure function, can be assigned to another core and run at any speed, and it doesn't matter what anybody else is doing because this thing is not depending on any global state, and it's not changing any global state. And so as we've come to the problem of having to schedule 6 cores, 8 cores, right? Which again, you can do yourself imperatively. You can say, okay, I'm going to assign different processes to different cores, and I'm going to deal with all my little blockers and my signals and flags to make sure I do things in the right order and that nobody's waiting around for the network when I was trying to render or whatever. But I'm going to do a lot of ceremony, and I'm going to underutilize my core potential. What's better is if the operating system can say, 5 functions are running, those 5 functions all have no side effects, I got 6 cores, these 5 cores, everybody gets a function, and that's it. I know I can do it because the way the code is structured, each guy can be, it doesn't depend on any other guy. Nobody's going to trip over anybody else's feet. Okay. So because we are now living with multi-core systems where we don't want to do all that scheduling ourselves, and because we're dealing with large data sets, where we only want the first 50, it's like, give me every star in the universe and give me the first 5 that start with the letter A, right? It's like, well, I don't actually evaluate every star in the universe, I just want to get those 5 that start with the letter A. And because virtualization and just-in-time compiling and target compiling has become more performant, we are now living in a place where the platform that we work on, especially app platforms, but this is true of game consoles and computers as well at this point, benefits greatly from functional development, where in the past it would have been a burden. And so that is why there is this interest in functional programming. Okay, so as I started getting into more functional development, I was working mainly in Unity, and I this is over the course of last year. I just started studying a little bit more in the formal math of it. I kept coming across monads, and I came across this interesting phenomenon, which is that, and it started in about 2012, the monadic thing, and I kind of got into it in around 2015. These very smart guys would say a monad is this thing that once you understand it, you can't explain it. But it's kind of like a burrito or a programmable semicolon. So I got a number, but you don't really have to know. Just do things monadically, and you'll see intuitively that they're much more elegant. Okay, and so I wanted to call 2 guys out here. So I ran into a series of what I'm calling bad answers to the question, what is a monad, and why do I care about it? Right, and the first 2 bad answers came from these 2 guys, Dr. Subramaniam and Martin Odersky, who have a good number of talks online, especially about Scala. Odersky is the developer of Scala, and Subramaniam is a very active developer in the Scala community. And Scala is a language that was developed to be a mixed mode. It's an imperative and a functional language, and its design motivation is highly, highly monadic. And so they have lots of examples of how to create monads in Scala. And in describing what monads are, they mention that they're an idea that comes out of category theory. And that first original joke I showed you there, it's just a monoid in the category of endofunctors. What's the big deal? Right? And they say, you don't have to worry about category theory. You don't have to dig into these into what monads really are. You can just follow these code examples, and you'll see them doing things more elegantly than you probably would have done them without this stuff. And that's all that's really important. So even though I think these guys are really, really great, and I really like their talks, I call that a bad answer because it's like, what do you mean I don't have to know? Right? I always kind of want to know. And so I've dug in a little bit into the category theory of monads, and they're kind of right. You don't deeply need to understand the deep math of category theory, but it does help to get the basic idea of what a monoid in the category of endofunctors generally means. So a monoid is a function family that behaves according to 2 rules. First of all, it's a function family that takes where functions take 2 parameters and they produce an output that is the same type. Okay, that's the first rule, and the second rule is associativity. That when you have several of them chained together, it doesn't matter what order you do it in. So the first abstract mathematical concept that we all learn is a monoid. It is addition in integers. You know, when you're in kindergarten, you learn addition in integers. 1 plus 2 equals 3, right? Every time you add two integers together, you get another integer. 5 plus 6 equals 11, right? So that behaves according to the first rule. And also addition is associative. If you have 1 plus 2 plus 3 plus 4 plus 5, it doesn't matter what order you do those in, you're always going to get the same answer. So addition is a monoid in that respect. And that's all that means. It's a function family where the output, where the results of the function put you back in the family. And it doesn't matter what order you do it in. Multiplication in integers and real numbers is another monoid, right? Every time you multiply two integers, you get an integer. It doesn't matter what order you do it in. Subtraction in integers is not a monoid, because even though subtraction produces all integers, so like 1 minus 2 minus 3 is an integer, the order in which you do it matters. So 1 minus 2 minus 3 is different than 1 minus 2 minus 3. Okay, so that's monoid. Endofunctor, for our purposes here, basically just means function, right? So basically, what we're saying is a monad is a function. It's a design pattern where that the products of the interface of a monad are more monads, right? So that's basically it. And it doesn't matter what order that you chain those products in. You will always get the correct resulting monad. And so order of operations doesn't matter, and that's basically it. All right, so that's the idea. That's sort of the categorical idea for what this is. Why do we care though beyond that? All right. Specifically, what this monoid is. All right, and this is the good stuff. Is an object which takes a value of type A. All right, so C++, Java, C#, object-oriented languages in general, an object. It's just a wrapper object. That's all a monad is. So like, for example, a monad that takes a type A, it might be integer, it might be string, it might be doctor record, it might be patient record, it might be SQL query, it might be any number of types. So let's say, a monad of an integer. All right, and then it defines just a couple of functions on itself with respect to that type. The first is called a return function. The return function is basically a constructor. It says, given an instance of A, right, return a monad where its value is that A. So if you had a monad of an integer, right, and you called it with a constructor with 3, your monad would now contain a value of 3. So it's just like a very simple value constructor of the underlying type, like you would have in any kind of thing there. The other thing, it also defines what's called a unit function, which is the default constructor that constructs itself with a default value, just so that you can make a monad without having to assign anything to it. And then, most importantly, this is where the juice is the bind function. Now, a bind function is going to be like a lambda in C#. The bind function takes a lambda that takes a type of your underlying type. So in this case, an instance of integer. Right, so you had monad of integer, and returns a monad of another type, or possibly the same type. So this here type B could be an integer, it could be a string. So for example, if we have a monad of integer and we want to convert it to a string, we would bind it to a function that returns a monad of string, and that underlying function would do whatever jazz you do to make a string happen in that language, and then assign it and make a new monad of string, assign that string to it, and now you've gone from a monad of int to a monad of string. All right, and they follow some laws, identity laws, that basically say if you make a copy of yourself, it's the same thing. And we are associative. So if you bind, if you have a chain of 3 or 4 bindings in a row, that it doesn't matter if you do the last 2 first and then chain to that result, or the first and then go straight forward. It doesn't matter what order you do the binding in. And so that allows for lazy evaluation and order of operation correction. Okay. So basically what we're doing here is we're setting up this chain that says I've got myself a monad. It's just an object that wraps a value. I have this interface that just takes a value and makes a new kind of monad for me. And so I can chain through that interface to a new monad with a new type that can then do it again and do it again and do it again. right? And this is basically a design pattern that's a rule for chaining functions in functional systems so that you can preserve state, you can do whatever you want, because each of these functions that produces a new monad, that new monad can carry forward information from the previous monad. You can use this for error handling. Like if I do a divide by 0, it can come in here and say, oh, you divided by 0. I'm not going to produce a rational value monad for you. I'm going to produce a number error monad. And that monad carries forward, and if you try a bunch of other stuff that you think I succeeded, that rational value monad or that error monad will say, yeah, I know you're starting to do further computations, but I'm just going to keep passing myself forward because there was an error way back. And I can mark where it happened. And at the end of this chain, it can say, oh, we got an error at step 3. Steps 4 through 9 did nothing but propagate the error forward, because that's what the bind function can do. It can say, oh, you actually want to work with this value, or do you just want to propagate forward the value that you sent me in? All right, so what all of this does is it allows functional programs to confront the imperative world, to say at each step, I'm making some kind of imperative decision. I'm changing the state of something, but I'm propagating those changes forward so that they can actually be executed on the system in some safe place and some safe time when everybody knows now state's going to change, as opposed to the way an imperative programmer would do it, which would be to poke it in place and change it along as it goes. Okay, so here's an example of monad object in C#, just to give you an idea of what I'm talking about here. You have a class that takes a parameterized type. You have an instance of that type that's your value, that's your private data. You have a copy constructor or a value constructor that takes a value, assigns it locally, and that's it. That's the return. You have the bind operation, which this is in C#. It basically takes a function that goes from an A to a monad of B and just calls it with that, right? And you can override this bind function for monads that do other things besides that, like error ones that might say, I'm not going to call the incoming function. I know that I propagate myself forward, so you just would override your bind function. Now, the thing is, for example, when you want to, when you basically want to add things together with a monad or whatever, you're always calling these bind functions. And I got another slide where we'll see a little bit more of that. The thing to keep in mind here is that this is not literal. In C# or in most other places where you go, you're not going to write a monad class and do things as monads. It's much more akin to a Turing machine. If it's more, rarely would you ever go and build a Turing machine to solve a problem, right? You're going to use a higher order thing. But you know that any computer program that you write that's successful can be reduced to a Turing machine, because we have that mathematical truth. It's like every computer programmer is reducible to a Turing machine. And I know the properties of a Turing machine. I know the parameters of one. So therefore I know the limits of what I could potentially do. This is a similar kind of thing. This is a design pattern where what you want to be able to do is show that the convenient way that you've done something can be broken down to this. Could you do it all with this monad class? Right. If you have like a data comprehension you're trying to do, it's like, can I take this class and write out a highly ceremonial series of bind functions that will produce the right result? If I can, then I know that I have monadic design. If not, because there's some side effect or there's some other thing, then I need to be very aware that I've broken monadic design. Okay, so if you want to learn a bit more about this stuff, there is a language that is explicitly monadic. It's Haskell. It's an up-and-coming language. Facebook is using it now for all of their data analysis stuff. It is a language that is explicitly monadic, and I would highly recommend it if you haven't had any time with it at all, because it's very, very different from a lot of the other languages that you're going to encounter. In Haskell, you have to lay out the type relationships for all of your operations first. You have to have a high-level design that's completely integrated before it'll even compile, as opposed to other kinds of languages that'll just let you declare variables and throw things in and try it, and does this thing set and give it a temp or whatever. No, in Haskell, we want to know what the high-level intent is first, and then you get to go write the implementation, right? And so in Haskell, everything is explicitly monadic. All of the libraries are called monads. They have an input monad and a list monad and a combiner monad and a writer monad and a reader monad, and everything's called a monad. And everything is under the hood in Haskell implemented with these kinds of bind operations. And so here's like an example of a monad that's called the +1 monad. It just takes, it has a value, it takes a function that just takes its own value and adds 1 to it. So when you call a bind operation on the +1 monad, with you will get back just a +1, that's it. The absolute value monad, similarly, takes the input, sees if it's less than 0, it returns the just monad for either negative A or positive A. Only positives, right? Now, all monads have one parameter in their bind operation. But most of us have to deal with things like A plus B, 1 plus 2, you know. And the way that we deal with that, with having multiple parameters, so you can have sometimes 15 or 20 parameters in a function, is with something called currying, which happens under the hood in Haskell, where you have an add function that takes 2 parameters. So you break it down into 2 functions. One is a function that takes whatever the current value of x is and adds it to whatever parameters passed in. And then you have a function that produces that value for any given value of x. So in add, you can see here that we're taking x and we're binding it to a function that takes an a and binds to a function that takes a y and adds it to a. Okay. Now, clearly, for a plus b, this is a ridiculously ceremonial and difficult to understand syntax. And this is why I compare it to a Turing machine, right? Is that you never really need to worry about currying out all your parameters in a real function. And even in Haskell, where all of this code looks like this and is all highly monadic, they have a syntax that is faster. That is just like, okay, look, you know, in this case do this, in this case do this, in this case do this, like a switch statement type of syntax. Precisely because monadic decomposition gets hairy and crazy looking, right? Even though it's highly valuable. Okay, so this, as I spent that kind of time with monads, working in Haskell, working in these other places, and trying to understand what the role of this design pattern is in a language that was designed with it in mind, as opposed to C# or Java, where they're just kind of getting around to these ideas. That the second sort of bad answer you'll encounter out there is that it's a programmable semicolon. And I'm not going to go too deeply into this, except for to describe that back in the old days when we had assembly language, okay, we didn't have macro instructions, you know, the way you do now for like printf and this for loop and all this kind of stuff that are setting up counters and talking to I/O and whatnot. We did things one instruction at a time. Move this out of this memory into this register. All right, now add 1 to it. Okay, now move it over there. Okay, now send this signal. And each of those was its own discrete step. And they were atomic. There was nothing more basic than move. Nothing more basic than add. You know, this wasn't composed of smaller functions. This was a primitive function of the computer. As we moved from assembly language to structured programming like C, where like declaring an integer, declaring an array of integers, doing a print, you know, scanning for input over a for loop, these are all multiple assembly language instructions. Right? So it became necessary for us syntactically to say, I want to have a blocker that says what you just saw should be a complete function in this language. And that's what the semicolon does. Declaring an array, printing, declaring a counter variable and putting in its checker and its incrementer. All of these are blocked out by a semicolon because the semicolon says what just preceded me is a 1 to 50 assembly language instructions that constitute allocating an array, that constitute printing and calling a library function, that constitute this, that constitute that. Okay, and the semicolon just stands in place, is the place that does that. And it's not programmable because everything that comes before the semicolon is programmable. So you write a bunch of code and the semicolon says, now go do that. In the monadic space, okay, and this is the answer for great good. And the reference there is, there's a book called Haskell Programming for, Learn You a Haskell for Great Good, which I highly recommend. If you're interested in the evolution of our software paradigms, you should definitely spend a weekend or 2 with Haskell, even if you're not going to go into web development, simply because it highlights this idea and forces you to use it. where other languages are. Like Scala facilitates you using it if you want to, but you kind of have to know what you're looking for. So it's a functional defined that allows the chained operations to propagate results without side effects or unneeded computation. The lack of side effects or unneeded computation has become a performance requirement now in the last few recent years. And the reason it was called a programmable semicolon is because in a monadic system, when you have like a value, and then you bind to another value, and you bind to another value, and you bind maybe to an error or whatever, that each of these steps here, the bind functions, like I'm going to take an integer to a string, to a patient record, to a this or to a that, right, is a piece of code. It's not a semicolon. And the things that are being blocked out in between are noun states, okay? So when we are doing verb-related programming, the states are stored in nouns. The verbs are in control of the nouns now, right? Whereas before the nouns were in control of the verbs. And so at each step, we want to know that we have completed a total noun state. And that's what a monad is. It's like an instruction in C++ or in C or whatever that is complete. This monadic state is complete. I'm an integer. This monadic state is complete. I'm a string. This monadic state is complete. I'm a patient record. Okay, and I'm guaranteed, and this is why it's also sometimes called a burrito. It's because it's a wrapper for an underlying propagated data value that once you get it back, you know you're in good shape to apply any other value. And apply any other value, and you're safe. You can keep propagating all these values forward. And so for that reason, it is worthwhile to look into a little deeper understanding than I was able to produce here, because it's an involved topic. And so I'm just going to leave you with a couple of recommendations or sources. First of all, Learn You Haskell for Great Good by Miran Lipovac. That's available online on a PDF for free. Check it out. Try a couple of Haskell things, especially if you're going into web development, big data, anything like that. You really want to be looking at Haskell. It's where the future's going to be. Monads for Functional Programming by Philip Walder of the University of Glasgow. This was the paper that kind of got this idea going for us. I think it's a couple decades old at this point. This is much more involved if you're looking at the computer science mathematics of it. It's not heavily categorical theoretical though. It's a practical paper that's like, here's how you can use this design pattern to keep your functional programs from either stagnating or going insane. Again, Venkat Subramaniam, Joy of Functional Programming. The one I would really listen to, and it's kind of the one that inspired me to do this talk, and I would have liked to have just made a commercial, is Brian Beckham's Don't Fear the Monad on YouTube. He goes into a more detailed explanation of the monoid step and the relationship between a monoid and a monad. He lays it out in 2 or 3 steps so that you can really see the value of this. And then he does some great examples in C#, showing the how you can use monadic design to validate large data operations. And then, of course, Martin Odersky at the Scala Initiative, and he's put together Scala, the language, which is intended for this mixed mode. It's not a pure functional language. It's not a pure imperative language. It's there for you to be able to use, lambdas and things like that, along with objects and managers. These are all fantastic resources, and I highly recommend you'll feel like you got like 5 years worth of CS out of just watching them on YouTube. And that's it. That is my talk. Thank you.
Time for one question.
Yes.
So as the number of transistors and cores in computers increases over time, do you see functional and monadic design playing a much larger role in everyday computer programs in the future?
Generally speaking, yes. As I said, because the biggest thing is that functional programming takes the responsibility out of your hand to have to manage global state sharing, and nobody is going to do that better than the OS at this point. And so we're going to be seeing greater and greater usage of the functional programming models in apps for that reason, because your code's going to be threaded. You want it to be isolated. So you're going to use design that says, I know that this function is not touching anything and nobody's touching it, so it can be, so the OS will notice that too, and it can be threaded. I don't see object-oriented development and the basic imperative model has won so much that there's no way that functional is going to completely replace it. It's using it in there's as I mentioned in the talk, there's targeted places where we don't have ways of being efficient with simple object-oriented imperative programming, where functional programming helps us be efficient, and that is in the use of multiple cores. That is probably the number one thing that's doing it, is use of multiple cores. The other thing is the processing of big data on web servers and things like that, where lazy evaluation just gives you so much speed that it's worth doing. So much so that, in fact, in the last edition of the C++ standard, Lambda functions are now in C++. So when C++ has introduced something, you know that it's going to be around for a while, because it takes them forever to do that. And C++ has got a rule that says you never pay for anything that you don't want in C++, right? And the problem is functional programming makes you pay for a lot of stuff that you might not want if you do it very casually. And so they took great care in C++ to say that when you're like invoking a Lambda function, you have to tell it every variable that you want to have enclosed in scope, as opposed to like something, a Lisp or something else that would just assume whatever's in scope right now is what you want, because it won't take the time to do that. So the fact that we're even finding ways of allowing you to maintain control of the metal and maintain imperative steps while creating these functional objects means that it's definitely a paradigm that's we're gonna be seeing it more and more. It's also fun. It's a really fun way to code. So.
Okay, thank you.
All right.